Hello, I'm Benjamin, Director of Engineering at Firebolt, and today we're going to talk about vectorized query execution and how it helps accelerate your OLAP queries. Let's start with writing a simple example query onto the board. In this query, we calculate the sum of revenue from our sales table, which originates here in Kirkland. All right, what your query optimizer is going to do is it will parse the query and then turn it into a relational algebra tree that our query engine can execute. In our case, we start with scanning the table sales. After that, we apply the filter. And the filter filters the city to be Kirkland. After the filter, we perform an aggregation, where we get the sum of revenue. All right. Now, we need to execute this algebra tree. The query optimizer performs a bunch of optimizations to turn your SQL query into the most efficient form possible. So it does things like predicate pushdown, join reordering, etc. For a query that's as simple as this, there's not that much to do. Once we pass the plan to our runtime, the runtime now needs to access the sales table and perform the actual computation. In order to do this, each operator sets up an interpreter. And this interpreter is then responsible to evaluate that respective query fragment. So we'll have one interpreter that focuses on the filter, one interpreter that focuses on the aggregation, and an interpreter for the scan itself. Now, historically, in query engines, you would pass a single row from operator to operator. What this means is that your sales table would start to look for the first row within the table, and then pass it on to the parent operator, the filter. The filter can now look whether the city is Kirkland. If it is, it again passes on the row to the aggregation. If it's not, then the filter goes back to the sales tables and say, hey, I need the next tuple. The sales table is then responsible for providing the next tuple. If that comes from the city Kirkland, it goes into the aggregation. And this way, single rows pass throughout this tree of interpreters. This isn't very efficient. To pass a single row throughout the tree, you need a bunch of function calls. Basically, the filter will call next tuple on the sales table, the aggregation might call next tuple on the filter, and you start jumping through your operator tree, evaluating individual predicates and so on, just on a single row at a time. This is bad for many reasons. A, you have a lot of function call overhead during query evaluation. On top of that, you have bad code locality. As you process a single row, you start doing some table scanning, then some filtering, and then some aggregating. Finally, this also isn't really good for cache locality. You don't operate on a hot set of tuples in your CPU cache. Instead, you always just take a single cache line from the sales table through your operator tree. Vectorized execution is a way to dramatically accelerate these big data OLAP queries. And instead of passing just a single row through your tree of relational algebra interpreters, you now pass batches of rows through your query plan. This means that instead of generating a single row, the sales table might now generate 4,000 rows. And then the filter is evaluated on all of these 4,000 rows at the same time. Afterwards, you might pass, let's say, 1,000 rows which made it through the filter onto the aggregation. Now, this is much better for your modern CPU for a few reasons. A, you don't have a function call per row, right? The filter doesn't go to the sales table to just request a single row. Instead, you push thousands of rows through your interpreter tree. However, what's even better about vectorized execution is that it's amazing for modern CPUs. If you actually look at how the memory layout looks as you pass data through your query engine, you will see that individual columns are made up of dense consecutive memory regions. So in this example here, you will basically have a block of a few thousand rows that contains your revenue integers or floats or decimals, and you will have the city itself. Both of these columns are put densely into memory. And what this means is that when we do the filter on the city Kirkland, our CPU can just iterate over this dense memory region. This is amazing for modern CPUs because it makes it simple to prefetch the right data, it leads to kind of very predictable data access, and in some cases, your compiler might even be able to auto-vectorize the primitive and insert SIMD instructions. In conclusion, by passing batches of a few thousand rows throughout our query engine instead of a single one, we're able to dramatically accelerate OLAP queries.